So S of 1 you got was 5.2. Can someone tell me exactly what that means for the interpret section? This is important. What's the interpret part? Henry, what do you got?
1 second, the person is 5.2 feet from home.
Excellent. Is 5.2 feet. Is it feet?
Yeah.
From home. Excellent. Fantastic. I love it. So then you're asked to do the same thing, but for S prime at 1. S prime at 1. Someone else. Can someone tell me what that is? What is it? 2.4. So can you tell me what that means, Zach?
Yes. And at 1 second.
Yep.
The velocity of the block is 2.4 feet per second.
So you can say the velocity, but you could, if you want to describe it, he's moving at. The person is moving at what? 2 feet. Is it feet per second? Yep. Away or towards home?
Away.
Yeah. And I think that means north, I think. North? Yeah. Ah, okay. So now this is what I want you to think about. You might have already seen it and you might have already started thinking about it, but evaluate S. Oh, this dot, there's 2 of these things now. So you're taking the derivative of the derivative. So you have velocity, and some of you have taken physics. So if you take the rate of change of velocity, what do you end up with? Acceleration. So this is the rate of change of velocity. So how fast is the velocity changing? So if you wanted to do S double prime of 1, could you use your calculator to do that? Absolutely. You absolutely could use your calculator to do that. How would you do that? Well, what do you plug in for y1? What was the function? It was, can someone read me the function, the original one?
-0.9.
You do math, and then what? 8, remember n deriv? And then it's going to look different for some people, but then what do you plug in right there? You plug in y1, correct? Y1, and then you do x equals what? X. So if you wanted to do the second derivative, what should you put there? Math. Which one do I use? N deriv again, and I put x again, but what do I plug in? Not right, sorry. What I put in x down there, but what do I put right here? Y2, exactly. Vars, y vars, function y2. You're taking the derivative of that one and making x equals what? X. So when we did this one, you know you can do vars, y1, and plug in 1, right? Like that? But you could also do, instead, you could do vars, y vars, function y2. This is the first derivative at 1. Oh, look, does that match what we got? When your calculator does that, 2.3999999, what's it actually? 2.4. Your calculator does a lot of rounding, does a lot of estimating. And then if we wanted the second derivative, what should I plug in? What's the only thing that changes?
Y3.
You just make it y3, exactly. Y3, enter, and you make it 1 like this. Hey, is that exactly? Yeah. Now I have a question. This function, the original function we were working with, is it really ugly or just a decently fine? What do you think? Could it be a lot worse?
Yeah.
It could be a lot worse, right? It could be a lot more complicated. It could be like a rational function. It'd be terrible, right? So could we do this one by hand? What do you think? Could we do it by hand? Oh yeah, we could absolutely do this by hand. Come on. Could you take the derivative of the function by hand? What do you think? Yeah, you absolutely could. If you have a calculator, should you use your calculator? Absolutely. Now remember too, what's the other thing in your calculator? Hey guys, what's the other thing in your calculator? Instead of doing each of these individually, I could have done table set, started it at 1 and maybe done a delta of 1, and then I do second table. What am I going to get on my first row? Oh, let's see if, oh, there we go. What did I get on my first row? 5.2, 2.4, and 0.6. You can do all 3 at the same time on your table that way. It's another way to do it. So what is acceleration? It's the rate of change of, this is the rate of change of what?
So on that, what you're showing right there is derivative.
This is the function, right? Sorry. This right here is the function, Nick. This is the function right here.
Okay. Yeah,
This is y prime, and this is y double prime right here. At 1, and at 1. So that's the function evaluated at 1, that's the derivative evaluated at 1, and that's the second derivative. Yes, correct. So it's the rate of change of velocity. So where do you generally feel acceleration? What's the one place you feel it? What's the most common place? In your car, when you're accelerating, right? And here's the thing. Your acceleration and your velocity, can you have totally independent of one another? Absolutely. So for example, right now, do you feel as though you're moving anywhere? No, you don't feel as though you're moving anywhere because your acceleration is effectively 0 with regard to the atmosphere around you, right? So there's a great physics question I think I told you about in that What If Mad Scientist book. Did I tell you about the What If book? Absurd scientific questions with serious answers. This guy wrote. It's fantastic. And he does like 50 of them. People email him all the time. He's a really famous webcomic. The guy who does XKCD, Stick Figure Comics. So one of the questions he leads off with is, what would happen if the Earth suddenly just stopped spinning? Like what would happen to me? Like what would happen? Like if the Earth just, nothing else changed, just the Earth stopped spinning, what do you think would happen? X squared looks like this. What kind of concavity is this? It's concave up. How can we show that? How can we prove that? Well, if f of x is x squared, can someone tell me what f prime of x is? 2x. Keep going. What's f double prime of x? 2. And 2, no matter, is there any x in here, right here? Is there any x right there? No. So it's always 2. The second derivative is always 2, which makes sense because it should be a horizontal line. 2 is always what? Positive or negative? So this is greater than 0, so this is always what? Concave. And does that match our picture?
Yes.
Yes, it does. Go ahead.
For finding the second derivative without a calculator, you can use the rule trick that you
Only if it's a polynomial, yes. Only if it's a polynomial, correct. In this case, is this a polynomial?
Yes.
So go right ahead, absolutely. So for example, this first one, is this a polynomial?
Here.
Yeah, so could we have used that shortcut?
Yeah.
Absolutely. It's debatable whether you'd want to because it's kind of gross. It'll be clearer in the future, like I'll give you something that's like a huge function over a huge function, and you just A, don't have the tools, but then B, wouldn't want to evaluate it even if you could. Basically, if you have your calculator, use your calculator wisely, okay? So let's look at this right here. Let's look at this one right here. Right here, I like this one. This is a fantastic one. What about where's it negative? Yeah, negative infinity 2. And where else? 0, 2, exactly. Where is the derivative positive? Where's the derivative positive? Where is it positive? C. Henry, can you tell me that one?
Negative infinity to negative 1.3.
I love that. Negative infinity to around negative. It's not too clear which one it is, right? It's around there. Like I would accept negative 1.5. You know, it's not clear.
Yeah.
Estimate, but it's not 1. It's a little bit to the left of 1. And where else is it positive?
1.3 to infinity.
I like that, 1.3. I like the symmetry. You chose 1.3 on both sides. I like that. That's fine. So I would accept anything around negative 1.3 and 1.3. That's fine. Where's the derivative negative? Where's it negative? If that's your answer, Henry, you finish it. Where's it negative?
Negative 1.3 to
Yeah,
1.3.
exactly. So if you said it was positive those other places, it has to be negative in between. Absolutely. Good. Where's the second derivative positive? Can someone different answer that one? Where's the second derivative positive? Kira.
From 0 to infinity.
Nice. And where's it negative?
From negative infinity to 0.
Exactly.